All right. Hi. How are you today? Yeah. Okay. So best time after lunch? The same as, early in the morning? Well, I think do we have any lecture past one? I don't remember. I normally don't like. But okay. So we continue our journey into knowledge representation and management. Today, the ambition is to cover the motivation for agentic development in general. So a little bit of taxonomy of agents and a kind of soft start with propositional logic, again, in the context of reasoning agents or logical agents. So the overall motivation. We are now, it's not that we are heading to or we want to be there. We are already in the situation where um, the computing is ubiquitous. So computing happen around us in all contexts of life. So we are deeply, or it is deeply integrated in our lives. So, and there is a term for this, ubiquitous computing. So, and if you reflect on this type of computing, the situation, this whole ecosystem, uh, it offers a support. It's if an object of computation is a user, human user, then it is a assistance in everyday's life. If the object of computation are other devices, robots, other computing processes, software, then again, so this ecosystem leads to effectivization of labor. And as you can imagine, so there is a need for global interoperation between different systems and subsystems. And but also from the point of view of data on which the systems is working on. So such systems work or act upon formally described profiles, intents or liking in the case of human endpoints, habits, so typical situations and such. So data is way more complex with respect to structure needed to represent it. Another point here I want to say is about the environment in which computations happen. So in many cases, compared to classical software created for addressing a single task, where the environment is rather static. So here we talk about highly dynamic and changing environment. So let us maybe see examples of what kind of ubiquitous computing I have in mind. Uh, so yeah, on real life applications. So for example, business process management. So again, so it's a general definition of managing business logic. So all processes are can be described as interaction between different resources. There are different tasks, and you need to do provisioning. So by computing. So financial services. Um, workflow management and such. So this is one example of intelligence demanding applications. So you need to take heterogeneous information into account. Grooveware, that's what we expose to every day. So if you use Uber or any other system like this, a system that's provide decision support. So it's interaction of many software components to provide a particular service. And so far here in these two cases, we are talking about maybe purely software systems. So it's pieces of software interacting with each other in a complex manner, acting on complex information that lead to execution of to achieving certain goal. However, there are such systems in the physical world. So the software can be embodied into mechanisms, and here we talk about interoperation of different mechanical parts or components. For example, in the context of intelligent industries. So now it's still a big deal. So it was super hot several years ago, or maybe it started like 10 years ago. This Industry 4.0 and beyond. So the idea is that industrial processes should be automated to highest degree to make the manufacturing more efficient, cost and resource efficient. An example which is probably closer to me, I mentioned it yesterday, large-scale mobile networks. In this case, the ubiquitous computing span across all examples that I have mentioned so far. So it's a complex network with certain business logic on the one side and down to particular equipment installed in the field, base stations, servers, infrastructure connecting base stations and such, user equipment, and different requirements meet first from the as user demands on achieving particular quality, and the business perspective. So how to first deliver quality and then increase the revenues. And then it all boils down to configuring particular devices. And as I mentioned yesterday, so these devices tend to fail due to different reasons. And so ideally, the whole ecosystem should operate totally autonomously. So far, I was talking about kind of computing surrounding or being embedded in different parts and together this digitalization would deliver a certain service. Now, I mean, more formally, if we define such system, we are talking about open distributed systems. And the characteristic of open distributed system is that they heavily rely on knowledge of specific domain or several domains. And such systems are capable of dynamically changing. And the difficulty here is that the main challenge here is that the components of the system to a large extent not known in advance. So And as such, we need a special architecture, a special approach to design software for such systems. And that's what I finished with yesterday. So you need this special architecture should support interoperability, collaboration between different parts, service provisioning between resources, and the important thing is that these resources are very, very heterogeneous by nature. So now, think about this system from the development perspective. So you all learned different programming paradigms up to this moment. So what's so special about developing software for such systems? What does it mean to program distributed, open distributed system? The objective here, again, apart from the actual functionality, the overall, the global goal is to achieve autonomy, autonomous functionality of the system. It is not programmed to do one thing. It's rather functioning by setting a goal to a system, and it is up to a system to figure out how to achieve it. So maybe I should stop talking for a moment and ask you why traditional programming approach or classical programming approach is unfit for such systems. So traditional, I mean, like developing a piece of software that does one thing. So using well, whatever programming language, whatever framework. So so what's wrong with traditional programming? So, and again, a little bit of putting you in the context. So when you develop a program, so you think about your data model, you think about algorithm. Touching from this point, so why it is not directly applicable in the context of open systems, open distributed systems? And in the meantime, I will check if I started recording. Oh, yes, I did. Are you in a after lunch coma?
When we do this traditional programming, I think everything is clear. I mean, we know we have a problem, we know how to achieve the problem in a certain way. And we have some tools to use. So I think it's kind of deterministic how to do it. And you just need to tell the machine how to.
But from the point of view of handling data versus algorithm that actually implements functionality.
You mean the operating systems?
Compare it to. Yeah.
Is it like data is changing all the time?
Yeah. Yes. But okay, so what I mean with this question, so is the following. So if you develop a program, a piece of software for performing a certain task, so what you actually do to a large extent, you create a computational process. And what do I mean by this? So you have data structures. So if you think, you normally have a domain. So you can identify data, and then you choose the algorithm to implement certain functionality. And data would represent facts, of course. So now think, if your scenario changes, what does it mean? So it means that you need to write an update to your program. So and what does it mean changes? In many cases, changes in the environment that a particular piece of software operates means modifications in the data model. So you want to add some new facts into the system. I mean, take any Windows updates, so security updates. So there is a threat, and then there is a bunch of people sitting and reflecting on how to address this threat. They come up with new additional data structures, and they do a patch. But virtually rewriting the computational process, which is packaged in this solid piece of software. And again, from the programming from the technological perspective, so the way how you approach the creation of software. So traditional programming lacks incremental modification of facts. So basically, starting from some facts, you may derive some new facts. And for open systems, and again, for large-scale distributed systems, we need an alternative approach. And this approach on very high level of abstraction is about separating the information, the data, from the way how the data is handled. So you decouple the processing of data and the data representation. And then the idea is that you make the processing, so the logic itself, the motor, the engine itself, independent on the domain. So you can basically put new data model while leaving the execution engine untouched, and the behavior of the entire system will change. So you see that's kind of two different approaches. And here we come to the definition of inference. So formally speaking, inference is a mechanism for learning facts from other facts. So many things that I will say today are very intuitive and logical, but I think it's important to kind of put it in the coherent context so that we are on the same page. Anyways. And here we meet another keyword, which is learning. So what is learning? What does it mean learning in general, in the context of AI, and in this context of dealing with facts? So what is learning? I mean, when you hear, yes, please.
This case, checking if the provided output generated the expected output or the expected outcome. So, and if it didn't, then we don't do that again.
Okay, yeah, fair enough. More ideas? In general, when you hear learning in the context of AI, there are different kind of flavors of this term. So what type? So what is learning actually? Again, starting from the high level, high abstraction level, we are we need to think about a system that has rather limited knowledge about the domain, or well, limited by design knowledge about the domain it operates. And then, and again, so the reason for this limited knowledge is very simple. I mean, in many cases, we will be talking about taxonomy of environments. In many cases, you cannot fully characterize your environment beforehand. So if, especially environment is dynamically changing. So, and in general, so learning is about getting better performance-wise. So you want to discover new facts. You want to incorporate these new facts in the decision making, and so that's it. Now, how to implement learning? So there are several approaches to it. I mean, the naive way, the learning can be implemented by memorization, right? I mean, is it a valid model? Is it the learning? I mean, when you memorize something, is it learning? It is learning. It's a valid learning. I mean, maybe it is limited in its capabilities, but it is learning. I mean, many biological intelligent functionality is done by memorization of certain stuff. And then the reasoning, the type of reasoning here would be reasoning by analogy. So you have seen something, so you and then you experience a similar situation, and you recall from memory. That's valid learning modality. However, learning is or learning by memorization. One of the major shortcomings is poor generalization. So if you just rely on your memory, so you always do kind of analogical reasoning. So if you don't do with this information with analogs, and if you don't use them for any further purpose, then your mental process stops there, right? So you need, in many cases, again, in order to, I mean, the true learning, what we regard as learning, is to understand the rules, the general principles. Again, a very simple analogy. You can memorize mechanically how to solve quadratic equations, I mean, with the determinant formula and such. However, if you don't understand the principles, what this determinant is, so that's, I mean, the knowledge remains rather mechanical. But then again, the rules, what to do with rules? We might extract certain rules about the environment we are operating, the world where we are operating in, and about this specific phenomenon, and memorize them. So again, so the problem here, well, there are too many problems. So the thing is that you cannot come up with you know exhaustive set of rules like fully describing a situation. Normally, and again, so memory plus rules, it helps to improve the learning, but memorization is not memorization of rules is still quite static. So again, this long story short, we need a process that derives facts from other facts. And that is the functionality of the reasoner or intelligent program. So here are typical reasoning tasks. So I mentioned before reasoning by analogy. So that's rather mechanical. So that's it's valid, but in the biological context, it probably corresponds to fast memory retrieval. So fast inference. In cognitive systems, we have two processes, like a fast decision making and a long reasoning, so a slow reasoning that actually do inference based on facts. But formally, reasoning tasks can boil down to well, this are a subset of all possible. So in the book you can find more. So make explicit information implicit. So you will work with an instance of this reasoning. For example, knowing that. So that is the scenario, a little bit of spoiling the content of Lab 3. Knowing that pizza or of type like margherita is a kind of pizza, and a pizza is a kind of food. So that's what kind of your knowledge about the domain, and being exposed to the fact that an individual eats margherita, but that's what you have as a fact. A reasoning could, so this make explicit information implicit, would be to complete the links so that a person eats food. So which is maybe useful in some cases, again, for certain functionality. Or a person eats pizza, just knowing that it is margherita. So that's type of, it's simple but needed type of inference. Reasoning by default, so consequences may be derived only because of lack of evidence of contrary. Abductive reasoning, so basically you decide on the outcome based on the most probable explanation. So for example, you wake up in the morning, your lawn, the grass mat is wet. So what is the possible, most possible explanation? And then in your kind of at your possession, you have several alternatives. So somebody like poured water on your lawn. There was a rain, or I don't know, something else. And most likely, so or using other facts. So you could score these different alternatives, and so the most valid alternative probably would be because it was raining last night. So that was about the requirement for the requirement for the functionality. So we need to decouple facts from the processing, and the outcome could be one of these reasoning types. But from the point of view of software development, so we need also a special approach here. So we need to be able to dissect like a global global problem into atomic functionalities. And this target system should have a modular design. And these modules, again, they should be placed into distributed computing devices and coordinate and integrate their activities to achieve certain goal. And that is the principle of a general approach, which is called agent-oriented software engineering. So, so in gaming in game development, so that's a typical approach to a programming system. But here we talk in the context of general systems or generic applications. So what is an agent? What is an agent, basically, for you? So if I just quickly remove the slide. So what is an agent?
It's environment, actuators and sensors.
Okay. Yes. Yes, correct. That's a formal definition of it. Yes, absolutely. Well, actually, this term exists in different domains of computer science and electrical engineering. And depending on in which context you talk, so it has a different, well, touches or flavors of the definition. In general, so we talk about agents that are able to, as you said, perceive environment, act upon environment, but also to communicate. But what does it mean from the software development perspective? So that's one of the sketches, against a very high level. At the end, we are talking about a kind of middleware. Again, middleware is an old term, but a system that supports interaction of agents. So such that when programming a particular model, you focus on very focused functionality. And actually, nowadays you take it for granted. So you work with LLMs or whatever. So you develop an agent, and so which does something. So you you already, for many of you, including me, we are on this top level, just focusing on the functionality. Underneath, however, there is a need for physical infrastructure that allows agents to communicate with each other, and so that we can transition from a single agent architecture to something which is called multi-agent systems. Right. Did you program any agentic system? Like, can you give examples of, if I tell you now, develop an agentic system for managing, I don't know, this or that. So how would you approach? Any knowledge of frameworks, existing frameworks?
Just in general, I would start with like different kind of agents there. So we have like knowledge-based problem solving. So
yeah. Well, it's not a tricky question. I'm just pulling for, state of knowledge you have if you had previous courses in which we programmed agents. Because I mean, some years ago, I had a course where on programming of this network programming of distributed systems, and there I used the multi-agent system as an example. So and again. As an example of infrastructure on how to implement this modular atomic pieces of functionality so that they interact. And again, so I will publish, of course, PDF right after the class. If you're interested, there are plenty of systems that was developed, since many years ago. That allow actually creating technical agentic systems. On the other hand, so here I'm talking about agents. Maybe an alternative software engineering framework or paradigm would be service-oriented architecture. So that's more kind of geared towards web implementation. So you have services running or accessible via HTTP protocols, but so ideologically, I'm talking about pretty much same. So in the service-oriented architecture, it is the web, which is the infrastructure for communicating between agents, but they not need to be services. So you can implement agents in many different ways. Right. So that's enough. And here, agents and environment. So let's maybe talk about taxonomy. A little bit about taxonomy. So how it is helpful, simply from the point of view of understanding what is the degree of difficulty of developing agents in given application scenarios. Again, here maybe I will be doing mainly talking, so not writing anything, but some of the terms are kind of self-explanatory. So agents could be, again, the thing is that agents could be anything. So they can be very restricted, not intelligent, doing a specific thing, but so agent is a generic term. So in our context, we are talking about agents with rich functionality, and this functionality falls into different categories as listed here. So autonomous, so that the agents should take agents totally independent. Reactive, so it should react on changing environment versus or reactive versus proactive here. So proactive here would mean that you the agent actively plan for activities and try to forecast the needed the target effect. Agents could be standalone, so just or self-consistent. So they do not need to interact with anything. They just operate in the environment. Like take a robot exploring in some remote place. However, again, more capable agents are those that interact, and moreover, not only interact by kind of one-way communicating, but also sociable. So that collectively they distribute tasks between each other. And again, the takeaway from here is that the more advanced requirements you have on your agent, the more complex is its internal implementation. Then also thinking about environment. So environment directly affects the complexity of agent creation. And here is, again, so very high level taxonomy of the environments. We have deterministic versus non-deterministic, or again, without going into detailed explanation. So all real world environments are non-deterministic, meaning that you don't know all the states the environment can be during the lifetime of a agent. Episodic versus non-episodic. So here, for example, you can think about developing an agent in a certain production process, so that repeats every certain time. And the agent is developed only to operate deliver functionality within a strictly defined period of time. So, and that means that it doesn't need to be aware of what is going on there. So it doesn't need to take knowledge about other episodes into account. Static versus dynamic, discrete versus continuous. Again, all real-world scenarios are highly dynamic, and in most of the cases, continuous. Yes, I suggest we. So that's enough for kind of agentic development. So we take a short break and we continue with introduction to propositional logic.
Eller visst är det bra?
Det enda man lär sig om man ska läsa
Nej, jag tror det var den andra feminister versus stochastic.
allt det där.
Nej. Men det var den där som man typ såhär, som man explora.
Noun versus unknown.
Ja, exakt.
Så
jag... Nej, det var någon som var lite det var någon som jag vet.
Det typ, han var bara så att det här är ett algoritmverkligen för mig. Så det är helt det där. Men det var typ labbarna kommer vara i 14. Labbarna kommer vara i grupp 3. Man kunde skriva en rapport till labbarna.
Eller alltså egentligen där
För att mycket utav vad det här går ut, vad det går ut, försöker att man har en lösning och så. För världens lösning, det bästa lösningen som man vill givetvis lösa. Nej, men det handlar ju om att man försöker effektivisera. Eller man kan det vara på något sätt bästa, men varför?
Alltså, hela kursen att vi ska se vad effektiva vad är.
Ja, det kan säga
Precis, det var tidigare som var program som punkter.
Det var exakt det han sa.
Ja. Nej, nu ska du förklara varför jag man har ju bara typ så här 0,1.
Ja, men man stannar
Det var så tydligen väldigt lik ut.
det var det. Skillnaden så när man hade schackmek. Ja. Det var något
Ja, just det.
men det är
Det är fan vad. Det är American.
Godkänt är 50-64. Nej, 5.
This week. Quite nice. Kan vi bara vara ingenjörs? Det var jaha, det är overtime. Det är overtime because där är ju såhär, nu har det change round in.
Att man har 85
Ja, alltså static är the environment does not change for the agent. Ja, men den ja, dynamic, då förändras din värld med oss. Ja.
Man försökte skriva kod på datorn. Skriv bara ord. Skriv bara, använder den här algoritmen istället för att försöka skriva.
Ja, fan. What's you like to
För annars så kommer han säga att det är det skulle fel.
Eller frågade Björk innan av er om de önskar av
Skriv bara
luckan.
asylligt.
Men I was the victim. I was the victim. Jo, jag fick
Det mesta då ska man genomföra.
varför måste göra exempel på.
Alltså typ skriver kod så mycket ord. Du skriver
Inte så specifika syntaxer. Vilka steg man ska ta.
Det var inget fel på hans avfyra. Okej. Så kollar jag, vad var det? Bilder och exempel.
Så båda kurserna.
Ja, så det var väl så för jag tyckte det var för gav det inte. Passions.
Men det kommer på det tänker jag.
Positions on basic level alltså.
Ja, det som är weird för mig är så kommer jag
Ja, det är tur.
och just tolka när det är så alltså så här
All right, shall we continue maybe? Here we go. Logical agents, propositional logic. The idea here, so the ambition for today is to kind of do a soft introduction and stop by the concept of entailment. That's a very important concept for reasoning, because based on, if we get the concept of entailment, then the next question is how to check the validity of models. So basically the procedure behind reasoning in propositional logic. And so what are the options there? So that we will be talking about tomorrow. But again, so I want to kind of connect propositional logic to our discussion about agents. So we learned that we need this species to be able to somehow program in a systematic way open distributed systems. And so again, if you look, this is the great definition of an agent as a piece of software, or I mean, we focus on the software access, software aspect of it, so not an embodied agent. So which is able to perceive the environment in which it is operating through a set of sensors. and potentially even affect the environment through a set of actuators. And then it has own performance measures somehow, how well it does. So altogether, it's summarized by this four concepts: performance, environment, actuators, and sensors. Now so the idea with logic and logical agents is to approach this otherwise very verbal scenario that we want to create a self-driving car, operating on roads without a traffic and such, having this set of actuators and this set of sensors. Again, just for intuitive understanding of the scenario, in a more formal way. So we want to approach again programming all this stuff. So to do so, we start with assigning symbols to our sensors, to which we see, and our actuators, to which we act. And as soon as we assign symbols, then of course, now you take a particular agent, it has a certain set of sensors being equipped by design again. And as such, so your percept is nothing more than a vector of symbols. So it's a vector. Again, for today and tomorrow, we boil down the type of sensors to binary sensors. So we will assign some truth values to whether certain event occurs or not. And then we need a procedure. We need to define a procedure what actually each action performs, and that is called transition model of an agent. So how to come from one state to another state by performing an action in the current state. And what we will do, so again, if you take a program, just not agentic program, any program, so the transition model is hard-coded. And then so you make a program to do a specialized action or function, and the transition model is hard-coded. In our case, the transition model is largely unknown. So we don't know all the possible outcomes. And the agent in general doesn't know which action leads to success. And as such, the goal, I mean, the functional goal of an agent is to complete the transition model through learning and logical reasoning. So you discover your environment by interacting with it. So now we come to the point when we want to describe a situation. So, or internally. So, and for this and many other we will develop an example which somehow relates to your lab 2. So lab 2, again, so I don't, is it open yet? Maybe not, no. But I mean, you will read about this scenario in the book, in the textbook. It's about navigating in the Wumpus world. So you have a beast somewhere, and you want to kill it, or you want to take. No, you don't want to kill it. You kill it eventually if you meet it. But your goal is to get a gold hidden somewhere in the environment. So here I kind of simplified that scenario to some bare minimum to explain some the reasoning procedure. So and in our scenario, so we again, so we have a discrete world. So an agent can take one step at a time. So it transitions from one cell to another, and it can enumerate. So it is a discrete environment, basically, so not continuous. So you can enumerate all the cells, and you can describe it by through set of symbols. So we start with just placing objects in this world and describing the situation. So we have a grid of rooms, IJ, and so now we want in our scenario that in some rooms we will have some poison placed. And so we to reflect this, we have this symbol P. So what are the possible situations where poison can be located in either cells 1, 2, 2, 2, or 3, 1. So in one of these cells. This is just detached abstract question. So when talking about logic and propositional logic, we talk about all possible world incarnations. I mean, where object of interest can exist in many places, and each variant of the placement we call a world. It's a separate world. So if poison appears to be in this cell, so this is one world. If in this cell is another world. But so we want to describe it. So our worlds, so we have a collection of situations, would be described by symbols corresponding to this statement. So by true, false statements. So how many possibilities are there? 2 to the power of 3, right? So we again, so we just asked ourselves about all possible variants of placing poison in 3 particular cells. Why not? So here are all possible situations or worlds that we deal with. So a model is then a possible assignment of values to variables of the statement describing situation. So here in this case we have 8 models. Oh, please disregard this arrow. It doesn't mean anything in this context. So now, these are just possible worlds in which we can appear at any given time. But now we want to make our mind about this world. So, for example, we want to make a statement or guesses, or in other words, we can state a hypothesis. For example, well, in our case, we resort to statement, so we will come to hypothesis further on. So we want to make a statement. There is no poison in cell 1, 2. So which of the models correspond to this statement? 1, 2. So those are the models, right? So all possible incarnations where we do not have poison in this cell. So let's take again another made-up statement, which says, so we claim that there is no poison in cell 2, 2, with coordinates 2, 2. Here. Again, to save time. So here again are all possible variants of it. So now, what we did, first we are able to describe presence of facts or objects in the world through symbols. And we are able to define a model, so possible variants of placement of this or this events or fact happening. And we are able also to kind of understand that only some of models correspond to certain statements. So now we have two statements. One statement is there is no poison in 1, 2, and statement number 2, there is no poison in 2, 2. Okay. So now let us overlay these two statements. So the models corresponding to two statements. So here we have a model, set of models for statement alpha 2, and now we put we overlay it with statements for the first statement. So there is no poison in the upper corner, upper left corner. So they will be intersecting. So let me see if I kind of jumped over it. Oops, sorry. Oh no, we are not there yet. Sorry. Sorry for that. We are not there yet. So now, we take it one step at a time. So far, we are able to describe objects inside the environment and make statements about it. So now we want to place ourselves, so the agents, into the world and add percepts to the picture. So here again, so this percept comes from basically assumption of the environment, so that if an object, a poison placed in a certain room, then in the neighboring cell there will be a bad smell. So there is a sensor of smell in an agent. So what are the then we can ask a more complicated question or a statement. So we can analyze what are the situations in which our environment can be, so that poison is located in either of these 3 cells, and it smells bad in a particular cell. So we extend our model definition by adding percept symbol, and want to visualize graphically this case. So B21 is true, and we don't know, so poison can be in either of the cells. So, and we talking about statement or a sentence alpha 3. So, which basically a set of all models describing this situation. So now we have something different, right? So we have a reduced set of possibilities. So this one becomes impossible model because we don't have any poison placed. So what to do with it? We now want to approach reasoning. So now being able to describe, and again understanding so the way that we need to consider all possible incarnation of a statement, we need to approach reasoning more formally. And for this, we come to the need of more formal logic or knowledge representation. This involves being able to constructing sentences using certain syntax. Okay. And sentences, I show more formal slide or slide with more formal picture of a syntax. But again, on the high level, so we have symbols and we have operations on signals. And our operations are logical operation, not, and, or, implies, and if and only if. So formally, again, so now I'm just pretty much repeating to the intuition that we covered here. So we need to define the truth values for the statement. And this, in other words, is called to define semantics. So, so we say that. So we give meanings to the symbols. What does it? What means to be true or false in a certain case? And then the model, more formal definition of a model, is a possible assignment of values to variables of a particular sentence. And then, so if sentence is true in certain model, then we say that model satisfies the sentence. So again, so here we have, so model is one specific incarnation of our scenario. And we have a sentence, so now written in a predefined, well-defined syntax with assigned meanings to each symbol. So basically, if we find a model, so one of these incarnations that such as in which the sentence is true, then we say that this model, this M, is a model of this sentence. So now we come to, again, an important definition of a knowledge base. So our knowledge base will be a collection of statements or sentences written in this syntax. And so these sentences will represent certain assertions that we know about the world, right? So some sentences will be fixed, so you don't need to derive them. So these are just given facts. pretty much rules of the game. And these sentences will be called axioms. And the reasoning will be about basically taking existing sentences and deriving new sentences. So now we come to a definition of entailment. So let me just again spell it out verbally. So we have two sentences, and we can tell whether one entails the other. Again, entailment is a kind of more formal term. So you can also probably use support as a synonym. So if one sentence supports the other sentence. So more formally, the entailment of between two sentences, so alpha entails beta, happens only if in every model in which alpha is true, the other model is true as well. In every model. So what does it mean? It means that so in the context of our knowledge base, in our knowledge base, we will have statements about the world. For example, there is no smell in 1-1, or there is no poison in cell 1-1. Why? Because I'm simply staying there. So I'm simply staying there. So there is no poison, and I don't feel any smell. So that I just reflect in my knowledge base as a sentence. And as you go, so you will populate your knowledge base with such sentences describing the environment. And at some point, so you want to make a proposition, or you want to make a hypothesis. So, for example, there is no poison in the cell next to me. I mean, you don't know it in advance, so you don't have this record in your knowledge base. And here you come to the need to check that your current knowledge supports this statement, or in other words, that your knowledge base entails the given sentence that you constructed. So your hypothesis. So now remember our alphas 1, 2, 3. So alpha 1 was about what was it? There is no poison in 1, 2, right?
Yeah.
So that was and alpha 3 was that there is a bad smell in the next cell in this one. So so alpha 1 was this set of models, right? And alpha 3 is a reduced set of models. So, in other words, in all statements, in all models where alpha 3 is true, alpha 1 is also true. But not vice versa. So this is the definition of entailment. So alpha 2, there is no poison in 2-2. So this and these models over here versus alpha 3 that we covered before. So there is no entailment between these sentences, because in all cases where alpha 3 is true, so alpha 2 is only partially, or is true only in one model. But maybe now we do the following exercise. Maybe that's a little bit mind bending. Let's make it more formal and maybe more logical with using formulas. So for this, I want you to show this. So that is, oh, sorry. Let me put it like this. So this is a table of logical equivalence. So again, no need to memorize it. You always can have a look at it. So about sentences being equivalent if they are true in the same set of models. So have a look at this. So they're also known under different names of properties of operations like commutativity, associativity. But specifically here, so biconditional elimination. So that's notice this. So what I propose you to think about, sorry, is the following. No. Yes. So on the one hand, so let's talk about entailment. So we have two variables. So P, again, so let's make up an example, like go to party. So this semantics. And M, so that would be, we give meaning of having money. And on the one hand, so we have a sentence, P, no, and so P and N. So that's a sentence in our knowledge base. Or any, forget about knowledge base, just a sentence. And on the other hand, we have the following sentence: P, if and only if N. So, question. Is this entailment holds? Or a second question, whether this entailment holds. Well, actually, it's you cannot invert the entailment size, but I will just write P. So M entails P and M. So 5 minutes. So think about it. So here is cheat sheet with formulas. So how would you reason about it? So what entails what? Now you can shout at me the variants of answers. How would you approach it? Can you just hint me on a procedure at least? So you need to resort to the definition of entailment. So that all models in which this sentence is true, in all models where this sentence is true, so does this sentence over here. So somehow you need to boil down to enumerating or understanding these models. But this other part is not an atomic formula over here. So you need, I mean, it's at least it's a little bit tricky to write all the models, all the models immediately. So, and by model, I mean that you have enumerating models. I mean creating truth table. So that's a primitive example. So you have P, you have M, and so let me just put it a little bit down. So you have P, you have M, and you have P and M. So possible variants again. So this is binary case, Boolean case. So it's 0, 0, 0, 1, 1, 0, 1, 1, right? And so the sentence evaluates in these models. So these are models. So, and this is sentence. And this is evaluation. So obviously it's 0, 0, 0, 1, right? So now, we need to do the same thing for the for this biconditional statement or biconditional sentence. Again, as I said, so writing the truth table for this sentence may be a little bit tricky right away. So you need to simplify it. So you take so P, if and only if M. So now you use first biconditional elimination. So it's equivalent to P implies M and what is it? M implies P, and further, so the implication, where is it? Yeah, so can be written as a negation or positive other term. So further And let's denote this sentence as phi. Just, I mean, there's a single symbol. So it's not P. What is it? Or. Always confuse this. P or M. And so that's the thing, and the other thing, so not M or P, right? So now it is more digestible. So if we have P, M, and our phi over here, so that's whole thing is fine. So now we can enumerate all the models. 0, 0, 0, 0, 1, 1, 0, 1, 1. Oh, sorry. And well, you can double check, but I think it is 0, 0, 1, 1, like this. So this is the truth table for the second part. So now, here it was 1. Now, coming back to our original question, so now you can check the entailments. So which sentence entails which? So now understanding the set of models and evaluation of sentence in this model, so you can say that in all models where P and P and M is true, which is a single model, the second model is also true. So it means that these entailments holds. But not vice versa, because here we have a second case where the model is true. So when you have something is wrong here, you should have corrected me. Of course it is wrong. Of course it is wrong. So what's wrong in here? You believe everything I say. Of course. So that is true. So no money, no party. Right? Money party, no money, no party. So that's easy. But what's the point is that we have another model where this sentence is true, while in the same model the other sentence is false. So the other entailment doesn't hold. So it doesn't support it. So basically, again, in simple words, you have this is your, for example, statement, and if it evaluates to true, so you then it supports even this big conditional statement. So let's stop at this point. Any questions? And we continue tomorrow with model checking alternatives.
Kind of positive.